Okay, it's time, I think, to get started. This is the part two of the session on advancing drought monitoring and prediction with applications to decision making. My name is Siegfried Schubert, and along with Anna-Rita Moriarty, we're chairing this session. I just want to remind you that we do have a cancellation, so the 10:50 slot is empty. So I'm hopefully encouraging people to think of the questions they want to answer, and so we'll have time to address anything that we don't have time before, including the previous session. If that fails, we're going to ask Eric Wood to do a song and dance, so please have questions. So our first speaker is Nolan Doskin, and he'll be talking about enhanced drought monitoring in the upper Colorado River Basin. He's one of our invited speakers.
And I advance with this. All right. It's true. Everything everybody said up here, you can't see the audience. It's awesome. I will look over there. You'll look over there. Everything will be fine. Please note we have 44 slides in the next 13 minutes. So we're going for it. Hold on. I just want to give you background. I'm from Colorado State University. We've been drought monitoring for a long time, recognized for 125 years of data collection at our campus weather station in the middle of Colorado State University campus this year. And we have seen fire and we've seen rain. Our office, the Colorado Climate Center, came into existence in 1974, and we promptly went into a drought period. You're looking there at a time series of drought based on a 48-month standardized precipitation index, only leading us up through the end of the 1970s there. So you see that drought period that shaped the Colorado Climate Center from its very early years. And we began routine climate monitoring largely for the purpose of drought assessment right away in the 1970s, the 76-77 drought shaping the beginning of our efforts. And in fact, two droughts squeezed in between, there we go, the 77 drought, the 81 drought, with some nice wet years in between, which softened their impacts quite a bit. But you see there that those back-to-back droughts under one governor administration, Richard Lamb, resulted in a Colorado State Drought Response Plan, one of the earlier ones for state governments in the country. And then this time series of April 1st snow water equivalent takes you right up to 2012. So you'll see that the 2002 and the 2012 drought were right in the family. So systematic coordinated drought has been an ongoing activity. I've been at the Colorado Climate Center since 1977, so I've been through quite a few of those droughts. And our drought management function is managed through the Colorado Division of Water Resources, a part of the state government. I'm a part of the university, and we have federal, state, local players involved in the process. Now, we've had many years of opportunity to gradually work towards improving our drought monitoring. It was pretty slow going in the 70s when we started. Just getting our hands on data were difficult. Now data access happens quite freely. Data quality isn't always what you hope it would be. But things that our group has done over the years helped develop a surface water supply index already in the early 80s in combination with the Natural Resources Conservation Service. That has been improved upon here in recent years, so it's on much smaller hucks than it was originally. We, years ago, customized the Palmer Drought Severity Index. We found the scale on which the computations were made were useless for in-state monitoring, so the modifications we made were simply to make it for much smaller areas, and came up with a way of assimilating the data to make that work reasonably. Not our responsibility, but the NRCS has been improving SNOTEL data collection and distribution for many years, and that's a critical element of drought monitoring in the western U.S. And then, for better or for worse, it's just scary for me whenever I go to drought conferences and see all the crazy ways SPI is used nationally, internationally, etc. But we developed the SPI during relatively wet years of the 1990s and have been using it for various reasons ever since. Other activities leading to improvement was our deployment and many other states' deployment of ag weather networks with an emphasis on measuring or estimating evapotranspiration from meteorological variables and adding soil moisture measurement as opportunity presented itself. And now we take this same drought graphic from 1890 and we take it up through 2000, and you see that much of this drought improvement work was done during years of relatively lack of drought. There were the 30s, the 50s, the 70s, and then we had this amazing drought-free period where we got to gradually improve our drought monitoring. Then along came 2002, hit like a brick. We thought we would be better prepared. We were not so prepared as we had hoped we might be. Watch this onset as depicted from the U.S. Drought Monitor as of the early 2000s. There was the end of summer of 2001. There was end of winter of 2002, drying in the Central Rocky Mountain region, and then watch this. By the end of summer 2002, Colorado, Wyoming was the epicenter of that drought. And it's interesting as we make comparisons of our drought this year to the drought of 2002, we could buy hay very easily in 2002 just by going to Kansas, even Oklahoma. This year, to get hay for livestock in Colorado, you had to go to northern Montana or parts of the southeast. Fascinating. So this drought situation of 2002, along with some previous droughts in Texas and the south, helped bring about the National Integrated Drought Information System. Authorization took place in 2006. The Upper Colorado River Basin was selected as one of the first pilot projects for NIDIS, and our group at CSU was selected to lead a monitoring portion of this pilot project with the goal of implementing a drought early warning system for the Upper Colorado River Basin. And we began that pilot by looking for what did people need, how did they make decisions related to drought, what were a group's drought vulnerabilities, thresholds, triggers, indices, what sorts of information did they feel that would make their life in the world of water management and drought planning and decision making go better for them, and then see if we could actually test a system that would put this to work. We're not going to go through this list, but this is just an example of some of the organizations that I sat down with over a period of months in 2009 to find out what did they need to do a better job being prepared for and responding to and minimizing the impacts from drought. Things we found was, not surprisingly, that different groups need different information, have different exposures to drought, different risks, different issues. And in the West, you often find that the real, where things really hit the road is through water law, water rights, prior appropriation system. And so the real ultimate drought trigger for many people using surface water supplies are essentially the river call system for when you're in or out of priority. Additional findings, interesting for reservoir operators, they all uniformly said, wow, our jobs are pretty easy during drought. We just released as we're required by the water law and prior appropriation system. Their real critical times came with high flows and peak flows, and where decisions made during high flows and peak flows really they were more likely to make bad decisions then that would lead to water supply reductions when they really needed it in future drought situations. So it was fascinating to hear. You tell us better information about high flows, we'll do a better job being prepared for drought. And again, most water interests who had reservoir storage says we're not worried about a one-year drought. 2 to 3 year drought is when we get nervous. Uniformly, a lot of people said we like the U.S. Drought Monitor, but not for specific decision making, just to find out how bad it is in other areas. We know how bad it is where we are. We use it to compare to elsewhere. and users wanted to get data easily from one place. Information requested, and we hear this time after time after time, you give us a better climate forecast and we'll be better prepared for drought 1 month to 2 years in advance. Those of you involved in prediction, there's your challenge. And a lot more information on historical prediction and interpretation, or historical assessment probability distributions of some non-standard variables like evapotranspiration, and reservoir storage. So we took recommendations to heart and began doing a drought assessment based on weekly updates consistent with the U.S. Drought Monitor and targeting the groups that we had been working with. And we began doing weekly written assessments and, in fact, webinars at certain critical times of year, trying to put conditions into historic perspective with credibility for a diverse set of users. Working closely with the Colorado Basin River Forecast Center, using NOAA resources to give tailored long-range climate outlooks for our area of interest. And away we've gone, doing enhanced monitoring ever since. This was the update graphics just used yesterday in our weekly assessment, showing very dry conditions again for the month of November. 2 different products for the same thing, showing November precip as a percent of average. It tells you that even observation-based inputs aren't always identical to each other. Snowpack for our current water year off to another slow start. So now when things start looking like 2 drought years, or in fact for southern Colorado and New Mexico, 3 drought years, then our user base becomes very concerned and worried. And of course the great climate integrator, Streamflow, and trying to communicate that using USGS products when we can so we don't have to develop our own. That was a 2-year time series. A big water year in 2011, followed by a almost not runoff season in 2012, and now near record lows going into the 2013 water year, and just hoping like all get out for some snowpack and runoff. Here is for the Yampa River, northwest Colorado. How's this for back-to-back years? The 2011 runoff, the 2012 runoff. Yippee. So 2012 wasn't the worst of record, but there it was with 34 and 77 and 2002. Reservoirs, we learned how to try to put reservoir information in better historic perspective for users to view. Individual reservoir operators know their systems well, but those who use them don't always know how they're managed and operated and what water is available for whom. This shows a 2-year time series for one of our largest reservoirs in Colorado, part of the Colorado River Bureau of Reclamation project, and you'll see that we failed to have runoff in 2002, and we failed to have runoff in 2012 as well. So it was insufficient to do the normal reservoir filling that occurs during late spring into early summer. And there's the time history of that reservoir over a 20-plus year time period. And then, of course, we work to deliver timely input to the U.S. Drought Monitor authors. This was our recommendations for this week, making some subtle degradation of drought conditions, mostly over eastern Colorado. We're waiting for snow in the mountainous portions of the region. This is an email that I put into almost every a slide I put into almost every drought presentation that I give. And this last year I gave about 50 talks to groups, anywhere from groups of 20 up to 400, many of them keenly interested in drought, and we keep adding to our distribution list for sort of personalizing drought information for users. Not enough time to talk about challenges, but in the Rocky Mountain region, you have this constant back and forth between the recreation and tourism industry, which is trying to downplay the impact of drought, versus agriculture and municipal water supplies that are trying to recognize and in fact sometimes even exaggerate drought for some benefits. We do have some issues working across state lines to really optimize information delivery and customization. That has to do with the fact that state climatologists, who I am for Colorado, often have our best connections in state, but watersheds cross state borders. So working within a watershed issue makes things more challenging. Just not enough time to talk about that, but we'll have that slide to refer to. Notice that if you do have a confident short-term forecast, it helps make your current condition assessment report more actionable. So even if you don't know the 1 to 4 month lead time, if you do know 3 to 14 days with some skill, you're more likely to act on your current drought severity and do decisions based on it. And then finally, one of our curious approaches is, when in doubt, give your stakeholders rain gauges and ask them to do measurements themselves. And this is our COCORAS network. Many of you are familiar with it. And it's, if you measure it yourself, you will take the results seriously and act on it. And I think that's the end of my talk.
Thank you very much. Questions? Anybody?
I see none.
None. Actually, I did want to just ask you, so you think, on one of your points that we need to look not only at drought periods, but wet periods, is that...
Yeah, that was a really obvious message, we're not just worried about drought. You tell us about the wet periods and give us the best information you can about that, and we're more likely to be better prepared for dealing with the dry periods. And it was a fascinating bit of input.
Yeah, it's good for us to keep that in mind when we focus on drought and such a wet day. So thank you very much. So our next speaker is Brad Lyon, and he'll talk about limits and uses of dynamical predictions of meteorological drought, our second invited speaker.
So I just advance with this. Just this guy here. For those of you who are standing, there's plenty of open seats here in the front. Okay. Thank you. Well, the basic motivation for this is that we now have the general technical capabilities to be able to produce global drought forecasts on a regular basis. But the devil is in the details, both in generating those forecasts and thinking about how people might use them. And this has implications, for example, for the global drought information system that WCRP is thinking about working towards. So some of the fundamental but important ideas that I just want to talk about in this brief talk are given here, that fundamentally the biggest constraint in terms of making drought forecasts is our limited ability to forecast precipitation. This, of course, is not to say that precipitation forecast is the same as a drought forecast. I mean, ultimately, when we're talking about drought, we're thinking of impacts, and to be useful, our drought prediction has to in some way be related to impacts. Of course, a key aspect of drought early warning is monitoring. But a critical bit of information that comes from the drought monitoring is the initial condition, which, whether you're looking at land surface models or meteorological-based drought indicators, provides critical predictive information. But particularly on a global basis, estimating the initial condition is not a trivial undertaking. And finally, I'll talk a little bit about using predictions, that it's not all about just having a reliable forecast for people to use it. I recently got the book The Signal and the Noise by Nate Silver. His subtitle is Why So Many Predictions Fail. Sort of in this context, from a user perspective, sometimes is why so many predictions fail to be used. So first of all, in terms of thinking about forecasts generally, I mean, there's been an explosion of seasonal forecast information in recent years. We have multiple global producing centers now that are producing seasonal forecasts on a regular basis. Here's an example for the current 3-month season. Precipitation departures, in this case given as sort of the best estimate of the mean anomaly or in a categorical forecast and so forth. But how would you go about using this sort of information? I mean, this is the best estimate. How would you go about making a probabilistic forecast based on this? I mean, ultimately, say if I have the question here, if you're in the Greater Horn of Africa working in a climate outlook forum, how would you incorporate this model data? Ultimately, you'd need access, say, to the hindcast. So provision of the forecast information by itself is not sufficient. You really need the additional information that's behind that. Of course, a key aspect of this, as mentioned, is that there's a limited amount of forecast skill. This is just an example trying to show that this is the percentage area in drought, in this case based on the 6-month standardized precipitation index being less than minus 1.5, but taken from a model run of precipitation, which is forced or using climatological seasonally varying sea surface temperatures. So the idea is that the atmosphere, the climate system, has plenty of internal variability that even without SST forcing, for example, you can get periods of rather expansive drought. Half the country in drought in this case are periods of multiple year droughts. So there's plenty of droughts are driven, at least in the model here, and no doubt in the real world as well, not necessarily forced by SSTs. So what we're looking for ultimately are forecasts of opportunity, primary opportunity being the ENSO phenomenon, for example. So in this slide, I'm trying to show that if I take a region of the U.S. Southern Plains and just take an area average, again, run a model, but this time with observed global sea surface temperatures, I've got 85 members of this model, and I run the model from 1950 to almost the present time. You can see this interannual variation across the Southern Plains. What's plotted here, again, is the standardized precipitation index. So brown equals drought episodes, green, wetter than average. You can clearly see the influence of ENSO there. What's along the bottom is what actually observed. So this drought was, in fact, predicted, and you can see that the model actually has skill. What's particularly interesting in terms of thinking about drought prediction are droughts of opportunity beyond just thinking of the ENSO connection, things such as why is this drought so much more pronounced in the model, say, than this was also a La Nina event here in the early 1950s. That's something that the NOAA Drought Task Force, for example, is interested in looking at from a predictive standpoint. From a meteorological drought prediction, and again, it's true of land surface models, the initial condition is being a critical element into the prediction. The SPI is an obvious example. So here I have, for example, a 6-month SPI, just these boxes indicate individual months, and say I want to make a forecast of that index 3 months later. So I have 3 months in common in the index, so clearly I have some built-in persistence into the index. And if you play with that a little bit and do a little more careful analysis, you can actually show that in terms of exploiting the initial condition, if you only use this information in the common period to make a prediction at the end of this 3-month period, you have much greater skill. So this is sort of the smartest, dumbest forecast you can come up with. In other words, it's only the forecast information is only coming from persistence, but by doing this sort of persistence, what we're calling optimal in this baseline sense, you can get significant skill. I can't get into all the details here, but it's highly modulated by the seasonality of precipitation. This is actually an example taken from California that if I have a start time in March and a lag time here, I can get correlations of 0.9 up to 4 months in advance. So basically, in terms of coming up with a global drought forecast, what the IRI has done in terms of looking at this SPI, they take their multi-model ensemble. We take a look at, on a grid point basis, if it's skillful after doing careful bias correction. If it is, say we're making a forecast of the SPI. If the model's skillful, we put in the forecast precipitation here. If not, we resort to our optimal persistence, and we generate a PDF of the SPI at each grid point and for each lead time. Whoops. Wrong way. So here's an example of such a forecast for the globe. So it combines the initial condition of the SPI along with forecast information. So what's showing here, I chose an example of the best estimate forecast initial condition in January of 2011, forecast for the end of April 2011. And because we have the full PDF, we can slice that distribution in different ways. For example, we can analyze the probability of the index being less than -1, or any value of the index you'd like. So what you're seeing here, for example, in this particular year was an important drought which developed in the greater Horn of Africa. We see that there's enhanced probability of that occurring. Some of this skill comes from the initial condition, but in this case, we can also show that some of that came from the ocean conditions. We don't have time to get into that here, and it picks up on things like the drought, of course, across the southern tier of the U.S., greatly enhanced probabilities of that occur. But if the initial condition, and just from a monitoring point of view, depends so much on monitoring, how well do we know what the monitoring state is? How well do we know what the initial condition is? So what I'm trying to get at here is I'm looking at the signal-to-noise ratio, actually signal-to-noise ratio -1, so that blue values show that you have a value less than 1, across 4 data sets that are publicly available over this period here. So we have a combined gauge-only set of data sets and these that merge station observations with satellite estimates. And you see immediately that over large portions, particularly say here in Africa, we have a very poor signal-to-noise ratio. It's not unique to Africa. There's other parts of South America and so forth where that's the case. So the fundamental problem here is that, the data sharing problem, even with the merged products, they're not particularly good when you have a limited amount of actual station observations to anchor them. Here's just an example quickly showing it's the same color scale for the signal-to-noise ratio, a different season, but for data sets that are available in real time. So the situation, of course, gets worse. So it's a real challenge just in knowing the initial condition for your drought prediction. One of the things that the IRI has been doing sort of on a regional scale and also on, I should say, national to regional scale, began in Ethiopia. For example, these are some stations that are available in real time, or at least publicly available, covering 90% coverage for this particular time. A handful of stations, but working with the National Meteorological Agency here in Ethiopia, they have access to something like 200 stations with complete records. So the idea in working with these guys is to say, well, how can we combine, for example, this station data, which they don't want to share, with satellite information to generate a merge product, which then they're willing to share. So my colleague Tufa Dinku has been working on this, and so he's done a careful merging of observational data with the satellite estimates, ending up with a product that's better than both of them individually. And because it's a gridded product, the National Meteorological Agency is willing to share that data, including in real time. For example, for drought prediction purposes, that would be very useful. In addition, because this is based on geostationary satellites, it goes back over a 30-year period to establish a nice baseline. Tufa has extended this work from just looking at Ethiopia, he's looking at Tanzania, Madagascar, and across all of the SILS countries, working with Agrimet, and this is work supported by the WMO. In fact, the data exists to do this Pan-African. It's not a technical constraint here. It's just a matter of really doing the work. So finally, in terms of just thinking about how the drought forecasts, we can come up with a global drought forecast. What's the context where we can think about actually using one? So I picked out an example of the Greater Horn of Africa drought and humanitarian crisis 2010-2011. This is considered probably the worst humanitarian crisis of our new century here. It resulted in famine in parts of Somalia and unfortunately rather high fatality rates. So in terms of background, basically if we're looking at the Greater Horn of Africa here, generally speaking they have a bimodal rainfall distribution where they have the so-called short rains from October to December and then the subsequent long rains from March to April. The short rains show a good connection to ENSO, where La Nina is associated with drought, for example. The long rains have historically not been linked to La Nina, but more recently have undergone a sharp decline. So this is precipitation anomalies across the region, and post-1999 have undergone a shift towards drier conditions. So this we're relating to, we can't get into it here, but to decadal variability, mainly in the tropical Pacific Ocean. But droughts have been more frequent in recent years, and this was being a particularly severe drought that occurred in this period. Of course, within this region, it was mentioned in an earlier talk that there's chronic food insecurity in the region, and the livelihoods of something like 80% of the population depend on rain-fed agriculture. So what happened in terms of this particular drought? If it's the worst to occur in this century, we would hope that our drought prediction system was able to capture that. In fact, it did. So here's the IRI forecast, for example, for October, November, December, from a September start time, already showing enhanced likelihood of below average precipitation. And the famine early warning system, as early as September 2010, was already saying this is going to have implications more than likely on the food security situation. And as time went on, they not only made stronger statements, they made analyses showing that how they anticipated this would be a severe impact. Nonetheless, in this particular case, despite the good forecast, despite the forecast being translated into food security terms, the response was not all that great until well after the catastrophe, if you will, developed. So this is just an indicator of donor support over time, starting in May of 2010 through October 2011, and these are when the FuseNet reports came out. So they actually were warning before the drought started. This is just a drought indicator. Pick your favorite indicator. This is the SPI 6 averaged across the region. So before the drought started, they were warning there could be consequences for this. As the drought actually developed, they intensified those warnings. But the donor support, while initially showing some ramp up here, actually they were waiting to see what happened to the second rainy season before they actually took action. And this was a costly delay. The one piece of climate information that ultimately became most used in terms of rallying donor support for this part of the region was simply ranking the precipitation. How bad is this drought compared to historical droughts? So for several regions here across the area, they simply, through FuseNet, ranked the data, and they found that some of these regions were actually the driest in the last 60 years, and that's something that resonated with the global press. They said, well, this is the worst drought in 60 years, and that's when the donor support finally came through, unfortunately, about 6 months too late. And this is explained in a recently released report about the delay in the aid, despite this being a well-forecast event. And these are typical kind of responses that you see more generally, that people have a hard time or don't want to act on imperfect information, information that's probabilistic, not 100% certain. Unfortunately, the catastrophe is certain, but you don't want to be in a reactive stance when you're thinking about reacting to drought. So the conclusions are basically, again, the technical capability now exists to generate global forecasts of droughts. I mean, the IRI has developed an experimental system for that. But the initial condition is critical, and it's very challenging to obtain that initial condition for the drought, particularly in, but not exclusively, the developing world. The IRI has some examples on a national and regional basis of how you can get around this data sharing issue to improve the initial condition. And following the improvements in the initial condition, in terms of improving drought forecasts generally, relies on better prediction of precipitation. So one of the things, for example, as I mentioned, the NOAA Drought Task Force is looking at, can we identify conditional forecast opportunities, or can we improve prediction capabilities for such things as the rapid onset or flash droughts, that sort of thing. And ultimately, when it comes to using drought information, there are many constraints on users using this, but ultimately, in terms of making useful information, requires a continuing, ongoing collaboration or interaction between those people who are producing the forecast and those who are ultimately going to use them. So thank you.
Okay, questions? I guess the reasons why it was the forecast wasn't believed, or that it was historically you had low skill there, or what
well,
is the reason?
Historically, for the for the short range, October to December, there's demonstrable skill in the seasonal forecast. I think one of the problems is that, particularly in the recent decade or so, the droughts have become more frequent, and so the idea was, is this just another sort of run-of-the-mill drought event? Even though it was well forecast, the impacts, they didn't trust that forecast in terms of the impact on food security as much as they might have. So unfortunately, they waited until there was absolute proof that this was a catastrophe before they ramped up on the relief.
Okay, thank you. Is it possible to turn the lights down a little bit for a few minutes? I guess there's no way. Okay. Well, in that event, so we now have, let's see, how much time do we have? We have roughly, I guess we're 10 minutes, or, let's see. 10, 15. Yeah, so we have about 10 minutes to just open it up to the floor for questions. Please, take advantage of perhaps questions you had from the previous session. And so, anybody? Yeah, okay. Yeah.
Yeah, Nolan's still here, I think, although I can't see him. But anyway, I like to kind of ask a question that is, or just sort of put out a point that is sort of combines the two talks we've just heard. So I think we've heard from Nolan that really predictions is what now people are looking for. And then, so on one hand, I'm wondering what kind of outlooks or predictions are provided by the NIDAS Colorado pilot, and then this ties in with Brad's talk that is really focused on predictions. Can we kind of use any of this kind of things that are coming out for like the Colorado pilot, for instance? So it's a question a little bit that combines the two talks, and I don't know if Nolan, you want to.
What's interesting is watching this evolve over time, where as recently as 10 years ago, there was almost no expectation for a skillful long lead multi-month forecast. And now there's been enough improvements in the short-term meteorological forecasts that a lot of the users really have an expectation now that the science community is, or at least should be, delivering skillful forecasts on the longer term. Now, we were just at a meeting together not long ago, and an IRI forecaster came up to me because I told him all the requests for forecast information we were having for the Colorado Basin, and he made the comment, well, we have no skill under this circumstance. He says, but our users don't know that, and in fact that's one of the products that we would benefit from greatly, is having an indicator that's simply a simple map or something that would show for the time of year and the region of the country/world where climate predictability is greatest and where your expectations should be low. Just that alone is useful in terms of people knowing how to use what's available. The basic predictive information coming out of the NOAA CPC, which those of us who know that we know how to work with it, but the average user still says, I know you can do better than equal chances with precipitation. I know you can. Well, if we knew we could, we would. But it's just communicating the uncertainty in those forecasts. But there is a much higher expectation. And there are situations, and Klaus Walter has customized forecasts for our basin, starting with CPC products and then developing both mostly statistical methods of improving that, but by providing finer scales, not just this national broad brush which is about all that forecasts are able to deliver at this point, but the users know that the outcomes occur at more local scales. And when the forecast can be delivered to distinguish between the mountains versus the downwind Great Plains, would make a big difference. So just being able to see where skill exists at what times of year, so that the users have an idea how to interpret the forecast better, that alone is a major step.
I think that's really a critical point, this whole idea of predictability and understanding basically, what aspects of drought are predictable at what times and what regions is really, I think it's a real issue for us that we haven't done a good job with that. And certainly, at this point, it becomes very model dependent. So whatever we do produce is going to have that aspect to it as well. So I just want to kind of relate to that is the idea of flash droughts. I think that's something that's been talked about a lot recently because of what this recent drought in 2012. And I think there's perhaps an area. We don't really understand it that well, but perhaps because we're beginning to, I think, do better at predicting things at this sort of shorter time scale, that there might be some hope that we can do that. And I think, Nolan, you mentioned that perhaps it wasn't as surprising as when we look back at what predictions there were, that perhaps we did better than we thought we had. And also Martha, I think, mentioned, I don't know if Martha Anderson is still here, about the connection with temperature, and perhaps because temperature is playing such an important role in these, that might be some hope that we can do better at these shorter-term droughts. So I don't know if there are any other comments, or how are we on time? So we just have a few minutes. I don't know, Eric, are you ready for your song and dance? Why don't you come up and we can get started.
So I'm going to talk today about our work that we're doing in developing drought monitoring and forecasting over Africa, but I will make the comment that our current drought monitoring over CONUS that we do shows basically that the whole country now is in drought. And it's pretty shocking when you go look at it. Usually, it goes green, yellow, and red, and dark red, and there's almost no green. I mean, there's a little bit, but not much. So that's going to make next year a little bit interesting. Even though they did open the skiing in the Northwest early. Development of an experimental African drought monitoring and seasonal forecasting system. We've been working on this. We see this as a first step towards a global drought information system, an objective drought information system, and we want to make it usable for users, decision making, and so that's part of the focus of what we hope to do. Oops, this one here. Okay, so my group, the timelines for our research is shown here. We've done a lot of historical climate analysis, going back in some parts back to the early parts of the 20th century. We do climate monitoring and forecasting, and we've taken this and done future climate projections, looking at CMIP3, CMIP5 model outputs, and one goal is to put this into a consistent analysis framework. But today I'm just going to talk about our climate monitoring and forecasting over Africa and what we're doing there and what we hope to do. The history of it, I mean, there's lots of people doing stuff in Africa, and there's, as part of GEO, there's activities, there's other groups, the Europeans under the Joint Research Center has activities, there's all these other groups. But we were asked by UNESCO to adapt our system that we've done over the CONUS region using, as part of our participation in the NASA NOAA land data assimilation system, they've asked us if we could go adapt our system for Africa and install it in some of their drought centers. We've currently installed it in AgriMet and ICPAC, and they want us to install it in another one. This was done without any funding except to have travel to go down there and install it and give some training. The milestones that we did, we want to adapt the monitoring system, we want to improve the data dissemination. That was very important for them. That they, UNESCO is a wonderful group to work with. They have people on the ground, they have relationships through the International Hydrologic Program, and they wanted to see how can this data get disseminated out there and how can it be evaluated. The very issues about, will users find it interesting and useful? So data dissemination, we're still working on some creative things, trying to develop some cell phone applications and enhanced local little sensor networks that will communicate with this and the satellites. So we had the training ones, and there's the assessment. So climate monitoring and forecasting, what tools do you use? On the left-hand side, these are sort of the standard stuff. We do some hydrologic modeling, there's some reanalysis, there's ground observations, satellite remote sensing, especially important in Africa where it's very difficult, if not impossible, to get ground observations in real time. And of course the regional global climate models, and you can also think, and there was some alluded to it by Brad, statistical relationships that exist. And all these can be put together to try and help the monitoring part and the forecasting part. This is sort of a block diagram of our monitoring system. We have real-time weather come in. We'll show you what that's based on. The initial conditions, we run continuously our land surface model that gives us initial conditions for the hydrologic part. It feeds into land surface model, so these predictions are objective. Currently we have one land surface model, but the whole plan is to go into a multi-model system. And the output of all that are these hydrologic variables, stream flow, drought indices, what have you, and then the management mitigation. So this is sort of the monitoring end to it, and you'll see this get augmented by this forecasting part in a few slides from now. So the land surface model generates the hydrology. We use things like the daily maximum temperature, daily minimum temperature, wind speed, precipitation. These get processed and massaged and used and put in as forcings into our variable infiltration capacity land surface model. You could put it into a different model. This is one that we happen to use. And as I said, we're going to use a multi-model system eventually, we hope. And then the outputs are evaporation, soil moisture, surface runoff, base flow. We route the surface runoff to create estimates of stream discharge at gauging stations and what have you. This runs at quarter degree spatial resolution. We would be happy to run it at a higher resolution. The data doesn't really support that, and that's part of the challenge. We use the TMPA's real-time TRIM, the multi-satellite precipitation analysis data sets at 3 hours. We aggregate up to daily. We apply some climatological bias correction because it's we do it in real time, and that just sort of is what it is. We could use the precipitation fields from forecast models. We do process GFS and use part of the output from GFS. So this gets done in real time, and we could certainly have a both as one. We just haven't implemented that due to personnel capacity. So we used the GFS to create the analysis fields to go create the meteorology, the surface meteorology that we need to go run this. And so that gets put into the system. And then we have drought products. And here's some examples here. There's a drought index that we use. So we've had a very long term, when we formed this, a very long background run for the hydrology, and we use that to create a statistical distribution on a grid-by-grid basis and month-by-month basis of what the distributions are, and then the soil moisture from the model is related to that, so it's a percentile. That has worked very well over CONUS and compares very favorably with other estimates that people have used of extent and severity of drought. So that's been fairly successful. Then we do the simulated discharge products. We took all of the, and we're talking about some thousands of gauges, data from the GRDC, the Global Runoff Data Center. We calibrated our model for these gauging stations and all the rest, and then because none of them report in real time, we then have simulated these products. That's the upper, this is the, this part up in here. These are different levels, they're quintiles, and so you can see where the actual prediction is relative to the various historical levels at that time of the year. And then this gives a deficit of the accumulated discharge from the beginning of the year to get a sense of whether they're in surplus or deficit. And then you can do basin average products. I'll give you a little example of how we pop up the basins. This is the rainfall, and this can go back to the beginning of our record, which is in the 50s. And it turns out when these data jump up, there's a little box there, and they compress it, and they can get a file which has all the information. So we do data sharing. So here's the drought index. We have an SPI. This is one that's based on the satellite one, and the historical that's been adjusted so that they're consistent. There's a big challenge here in doing that. And we were partnering with the French to get the SMOS soil moisture index, and for some reason that link is broken. And when I see Jan Kerr in a couple of weeks in Belgium, I'm going to ask him, why has this broken and we don't get a data feed anymore? This is what the page looks like, the page. You'll notice up in here there's different flags. It is totally multilingual. We actually have Arabic up there, and there's French for West Africa, there's Chinese for the new owners of Africa, there's English, and we can put other languages in there. It's quite simple to do. This gets updated. It lags by about 3 days, and there's a user interface in there which we can take a look at. So here, this drop-down user interface, the various capabilities that are currently there. It can animate hydrologic variables. In here you can put in different time periods. There's over 800 basins that we have, and some you'll see this in a minute, that they can pop up. There's lots of user control. You can zoom into regions because we use a Google Map interface, and the data goes back to 1950. And so here's an example of the precipitation. If you did it, you'd get that for the day. Or here's a evaporation, evapotranspiration in there. The drought indices there, and we're going to add some others that we'd like to do. We just haven't have personnel capability. And here's the basins in here, and for every dot is one of the basins or various sizes from the GRDC data set. And the green and the blue and the dark show wetter areas, and the reds down there, the hotter ones show drier ones. And so this actually shows, this is from earlier in the year that, in fact, West Africa had record rains this year, and in some places record discharge levels. And that was, in fact, reported by Agromet and just confirmed what we were getting. So Horn of Africa, here's an example. You click on that, on one of these, the basin jumps up, and you can see all the various information that you can get in here for different time periods, including basin balances and different variables. And so we hope it'll be user-oriented, and you can get some maps. This is the drought indice for that period that jumps in there. Monitoring, here's what the prediction system looks like. We're just building out. We have done all the hindcasts, and for all the hindcasts for 800 gauging stations, we have multiple, we have single, mostly we use CFS V2, but we'll see some results from the National Multimodal Ensemble. We do Bayesian merging, we do downscaling, the same what we do over CONUS, and then it feeds into the hydrologic stuff. And so here's seasonal forecasting, here's some initial products, here's SPI 6 for 2011. These are observations here. Here's a National Multimodal Ensemble, each equally weighted, and these are the various models that came out, and some do. None of them did really well in the Horn of Africa, but I'm not here to talk about forecast quality for the moment. And here's 2012, and you can see the very wet parts in the observations in the western part. You can see this in Central Africa. They had some dryness that was picked up by almost all the models. Up in here was a little bit too dry in some of them, and here's the multimodal ensemble. And so that's one part. Here's the hydrologic seasonal forecasting. The goal over here is to do not only just the maps of forecast of soil moisture, drought indices, but also to look at the basins. And here's some examples. You'll see the spread. We'll have some spreads on the ensembles as it moves out, and the simulated discharges. And here's a little example we put up here for this one basin going into the Horn of Africa. Transfer, Agromet, and ICPAC, it's very important to work with these communities to transfer to their portals so they have ownership and they can play with it and they can assess it. And the training is another real challenge we have to go work on with UNESCO, which we're trying to figure out how to do that. So plan future work, and basically we see this as a transition to a water cycle monitor and not just a drought forecasting and monitoring. Short-term, seasonal forecasting, add that, simulate real-time meteorological data if we can. Medium-term, other remote sensing products, vegetation, evapotranspiration, groundwater. I've had long discussions with Martha Anderson, which have hasn't really progressed except through desire to see if it can happen. Increased accessibility, better interface, and we can expand. This is totally scalable to the world with the same platform, and we plan to do that. Long-term, tie this into some modeling issues, spatial resolution time, and tie this into crop information that goes there. But all of this stuff has been done without any funding that has been directed towards doing this in Africa. And with that, I thank you. Are there any questions?
Okay.
No, it doesn't.
Okay, I think this is great. Are you starting to get some feedback, perhaps to start to sort of evolve your products?
Yeah, we have someone coming from ICPAC who's going to spend some time in January, and we'll get some feedback. My sense in West Africa, since they had so much rain, they weren't worried and looking at drought, which is not unusual. But I think that in the beginning of the year, when we get some ICPAC visitors for a month, we're going to get some more feedback.
Okay. Thank you. Oh, go ahead. Oh,
I had a question for you, Eric. So my question was actually two parts. First, what is the requirement of uncertainty in your predictions from the users, in terms of skill maps and uncertainty, probabilistic uncertainty? And the second part was, how are the monitoring products being used?
Well, that's the real sort of rubber hits the road stuff. We're trying to understand, and UNESCO is very interested in understanding how are users going to use it, and this is part of of what Agromed and ICPAC need to do in their interface with UNESCO. I mean, we're talking about communities that can't articulate what their uncertainty requirements are. We're talking about very local subsistence agriculturalists. We're talking about ministries that have low technical capacity that need help. It's a real challenge. It's not like going to the Colorado River Basin where they have a whole list. They can't even fit it on one slide unless there's 10-point font and all the interested users, and they're all very interested. We're talking about a different situation.
okay. So our next speaker is Amir Agakuchak, and he'll be talking about climate change impacts on drought severity, area, duration across the Southwest United States.
All right. Good morning, everyone. Before I start, I'd like to acknowledge my postdoc, Zhengchao Hao, who did only 99.9% of the work. So I start with the motivation. Here we are looking at the 2007 drought. It was a major drought, both in western and eastern United States. And you see here, how do I get rid of this one? Okay. On the eastern U.S., we have drought number 1. I call it D1. It is not a drought scale. It's just drought number 1. And in the western U.S., we have drought number 2. If you look at the average severity here based on SPI, for example, the average SPI, the two are quite the same. You end up with something like minus 1.4. But if you look at these two events, the one D1 is much larger. It's around 50% larger. So now the question is, if you have two different drought events with the same measure of severity, one much larger than the other one, are they the same in terms of probability of occurrence? Are these two, do they have the same probability of occurrence or the same return period or not? So current drought indices, SPI, SSI, or almost all of them, they are based on deficit in climate variables or hydrologic variables, deficit in precipitation or soil moisture. They do not include physical properties or geometrical properties of droughts, like spatial extent. And now we argue if you have two different droughts with the same severity, but one much larger than the other one, they should not be treated the same. They should not have the same probability of occurrence or return period. In fact, a much larger drought should be considered as a more severe drought event. So now the idea is, okay, how do we include this into our drought analysis? And then how would be our, for example, climate change analysis be different if we include spatial extent? Okay. So here we are not proposing a new index. I think we already have a lot of indices. It's just a different way at looking at our currently available indices. So if you have 50 years of data, you can look at, for example, fraction of area under drought for the same data set that you have, you can get your mean severity that could be just mean severity or mean severity above or below a certain threshold of, for example, S0. And then you can look at, for example, the joint return period or the joint probability of occurrence of drought with a certain severity and a certain area or fraction of area. So this is, for example, a general equation for joint return period analysis. And an annual scale mu would be 1, and the denominator is actually the probability of occurrence of a drought with a certain severity and a certain spatial extent or size. So we tried looking at joint return periods of droughts using climate data here, 16, CMIP3, hydrology projections. These data set, these climate models are bias adjusted by Maurer et al., available for the Western US. In this study, the baseline is 50 years of data, 1950 to 1999, and the projections 2020 to 2069. And we're looking at 6-month and 12-month standardized precipitation index and also standardized soil moisture index. And soil moisture is also a product of the hydrology projections that comes out of the WIC model, I believe. So the study area, the Western US, the data is available online to public. So if we only look at drought frequency, just the number of droughts, for now, let's forget spatial extent. If you look at the change in the number of drought occurrences in the Western US, this is what we get. So for example, including all droughts, everything longer than 1 month, you will see, for example, 2.8% change in the projection period based on 6 months SPI, around 4% based on 12-month SPI. For longer-term droughts, you see larger percentages, like around 6 or 7%. So this has been shown in some other studies as well for the US and for other places. But we want to go beyond that and look at the spatial extent and see how that would change if you bring spatial extent into analysis. So here is how it would look like. So this figure is generated based on precipitation data, 6-month SPI. Blue is the baseline period, and red is the projection period. This means that if, for example, in the Western US, 30% of the country is under drought, and the mean severity is around minus 1.5. By the way, Western US is large, right? So we're talking about over 1 million square kilometers, probably nearly 2 million square kilometers. Western US, that would be 30% of that would be already over 1 million square kilometers, probably around 1.5 million. So it's a large area, and a large area with a mean severity of minus 1.5, that would be a severe event. So it won't be a very ordinary event. So 30% with an average intensity of minus 1.5, that would lead to a return period, joint return period of 40 years. That means probability of occurrence of 0.025 or 2.5%. So this is based on the baseline data. If you do the same analysis with the projection period, again, 30% of the Western US under drought, the same severity level, again, minus 1.5 here, that would lead to 30-year return period. That means probability of occurrence of 3.3%. So this is a pretty big difference, around 10 years in the return period analysis of a severe drought. And as you can see, of course, for larger fractions, this goes up. That means a less likely and less likely drought event as you move forward in the x-axis. For more ordinary droughts, like here, let's say 20% or 10% of the Western US under drought with severity levels of minus 1.1 or so forth, the droughts that we see very often, there is not much of a change. So based on at least this analysis, by bringing spatial extent, you will see some things that we don't see from just frequency analysis, looking at the number of drought events. Apparently, if we believe in our precipitation projections, and you know what I mean with that, if we trust our precipitation projections, that means basically in future, as you saw in the previous slide, the number of events, we are talking about 2 to 6% or even 10% of increase in the number of droughts. But in terms of spatial extent, based on future projections of precipitation, this is on mean of 16 climate models, we would see larger drought events for the same severity or the same probability of occurrence. Our droughts would be larger in terms of size. Ideally, you would like to see this pattern for different durations of your index. Here, this is 6 months SPI. This would be the same analysis using 12 months SPI. Again, more or less the same pattern. Of course, the numbers are different here on the return period. Again, the same 30% of the US under drought. That would leave us with around 20-something years return period. The same in the projection period, that would be around 10 years less. That means it happens more frequently, at least theoretically. Again, at shorter, at the more frequent events, if you see throughout this curve, you don't see significant difference in the projection and baseline period. That indicates if you do statistical analysis of return periods or probability of recurrence, bringing area into the analysis will make a significant difference in your final outputs. Now, these two were based on precipitation, but soil moisture tells a different story. Again, these are soil moisture data out of a land surface model derived by precip projections, and depending on how reliable we believe our precip are, these are even less reliable theoretically, right? So you run a model based on precip projections. So they are definitely not better than our precip data. So if you look at soil moisture patterns and do the same analysis, for both severe events and events that we see very often, you don't see much of a change, at least in our projection period relative to the baseline. And this pattern is the same as we move forward to longer time scale. This is 12 months standardized soil moisture index. And in fact, it's quite confusing. So if we believe in our soil moisture projections, our model outputs, that means that in terms of size, this is relative, right? This is just fraction of area. So in this range, we see more drought events, and in this range, from 40% to 50% less. So again, the point here is not to actually quantify these differences and say whether we're going to have more droughts or less droughts, or what type of size of drought we will see more. The point here is to see the differences when you bring areal extent into probabilistic analysis of droughts. So now, so here, remember we noticed different patterns between precipitation and soil moisture. Now, if you look at, again, only frequencies, precip separately and soil moisture separately, you will see also different structures. So on the left, you have SPI-based. This is just frequency, number of drought occurrences, and the scale is percentage change in the projection relative to the baseline period. And on the left, you have SPI. On the right, you have soil moisture. And of course, you see very different patterns. And the reason is that, well, soil moisture involves land surface processes. You get this heterogeneity of the land. So precip and the meteorological scale, it has a certain structure. And then when it comes to the ground and it turns into soil moisture, you have the land heterogeneities, and you will see a completely different pattern. So that's one of the reasons that you see different analysis of area when you do you look at different indices. So this is basically the same analysis at a longer time period. So the previous figure was based on kind of short-term droughts, 1 to 3 months only, and the second figure here is based on 6-month drought or longer, not the duration of the 3 months SPI or 6 months SPI are the indices, but here we are looking at the frequency of droughts that occur longer than 6 months. In this figure. So to summarize, basically again, we noticed that, for example, if you do aerial analysis using SPI, you will see that for the same area under drought, the return period of future drought events will decrease, or probability of occurrence will increase. And with respect to a fixed return period, the area under drought will increase under climate change scenarios. But that's not really the point. The point of this study is, in fact, bringing aerial extent into drought analysis is important. And we cannot assume, and we need to basically build models that can integrate physical properties of drought into our drought severity indices. Thank you so much. This is the team. A couple of people is working on drought in my group. Thank you.
Any questions for Amir? This one? Yes?
I'm sorry? Well, this actually includes multi-year droughts as well. So let's say you look at SPI, 6 months SPI, right? You have 50 years of data, and when you do the analysis, that includes actually everything that happened in that 50 or 60 years of data, right? It includes multi-year droughts.
Okay. Thank you, Amir. Our next speaker is Lifeng Liu, and he'll be talking about CFS version 2 driven seasonal drought prediction over the United States.
Good morning, everyone. We already have a lot of talking about drought indices. And so in this talk, I'm not going to do that. We're going to focus on drought predictions. I would like to acknowledge my co-authors at Michigan State University and at Chinese Academy of Science. And of course, I have to thank the funding agencies, including NOAA Climate Program Office through the CTB program and MAPP, MAP program. It's not moving. Oh yeah, okay. All right, so we've already seen that in the last 2 years there's severe drought in Texas and in the upper Midwest, and there's a devastating impact on agriculture and the water resource. So what our research focus on is actually to improve the drought prediction over the United States, so we can provide useful information for decision makers. And so in this talk, I'm going to be talking about our current research progress and some results. Now, I'm not going to show you any old results like what we did a couple years ago. And so since this is a research in progress, we have some preliminary forecast examples, and you'll get a taste of that. And then I'm also going to mention some outstanding research issues. More information about our current research is available at our website, and also you can, you can get more information on this site. You can also get most up-to-date forecasts at this place. So which drought are we talking about? Here we really focus on the agricultural drought. We're looking at soil moistures. We're not. Of course, there's different aspects of drought. There's the meteorological, there's the hydrological, and the socio-economical drought. And in order to obtain the soil moisture information, in this case, we're going to rely on the hydrological model, one of them being the VIC model, the variable infiltration capacity model. For this hydrological model, when forced with meteorological information, precipitation and temperature, it can help us to determine what soil moisture is and stream flow and snow water equivalent and other things. So with this, what we're going to do is instead of looking at the soil moisture value alone, we're going to through this talk, we're going to use soil moisture percentiles, which is basically you rank the historical soil moisture over 30, 50 years, and then look at what is the percentile value of your current situation. If the percentile value is lower than 30%, then it's basically corresponding to the D0 category in the U.S. Drought Monitor. If it's smaller than 10%, then it's corresponding to the D2 category in the U.S. Drought Monitoring. And throughout this talk, you're also going to see colors. We're basically following the same color scale when you see maps like this. Most of this work was done a couple years ago. Well, the foundation was built a couple years ago when I was in Princeton. Well, Eric gave a very nice talk talking about the drought monitoring and the prediction system over Africa. And now we're still using this system over the U.S., over CONUS. If you look at these as a timeline, and here's the time on the forecast, before the time of forecast, we're using the real-time observations, including precipitation, temperature, to drive the land surface model that will give us the current condition. And if we put the current condition into historical perspective, that will give us the current drought monitor. Now, the current condition can also be used to provide initial condition for the forecast period, and with the same land surface model driven by some sort of precipitation and temperature time series, you would be able to get predicted hydrological conditions, and you can also do the drought prediction. So the question here is what type of precipitation or temperature time series which we're going to use, and we are trying to develop and improve the pre-processing scheme that we can take CFS V2 operational seasonal forecast in an ensemble mode and put that into the hydrological system to get our drought prediction. Now, to do that, there's certain challenges. One of them is look at this over Michigan. If we try to run a model over Michigan, these are the grids that we're using at 1/8 degree. But in order to provide that information, what does CFS give us? It's roughly at about 1 degree at the moment. So in order to go from 1 degree to 1/8 degree, we need to do spatial downscaling. And in the past, people have already used spatial interpretation, and also statistical or dynamical downscaling. In our research, we use high-resolution historical data to resample and produce spatial coherent patterns in the spatial downscaling. But we also work with bias correction schemes, because all these models, they tend to have their own climatology, so we have to correct those. And the method that we are developing, we have developed but still continue to improve, is the Basin merging technique. With the Basin merging technique, the advantage of this is it does not only do the spatial downscaling, but also do the bias correction. It also consider explicitly the scale of climate forecast. Now, consider if CFS V2 has no scale at all, what's going to happen? I mean, if you just simply do downscaling, you will get garbage in, garbage out. So what we're trying to do is trying to consider that. And the formula itself is actually pretty simple. So what we have been doing is, in the past, at any grid, we're going to take the climatological distribution from that grid, and we're going to take the model prediction, and then we merge these two distributions to get a posterior distribution of temperature and precipitation at monthly level. So we're looking at monthly T and the P. What is the posterior distribution of that? Then we're going to take samples from that distribution to generate individual ensemble members. To do that, we select historical rank structures, which is basically historical temperature and precipitation patterns. And we use that pattern to generate time series over the entire forecast domain on a daily basis. So now we have, in the end, we have adjusted the daily forcing time series to force our model. Now, the advantage of these forcing time series is it will have a coherent, it has a consistent spatial structure similar to something, some events happened in the past, but also satisfy the posterior distribution derived from the Basin merging. Now, what's been happening in the last few months, we have upgraded the real-time forcing from NLDAS to NLDAS 2, and we also upgrade the climate forecast from the version 1 of CFS to CFS v2. And we're also developing the capacity to implement multiple land surface model. The focus of the research in the past was actually on the improving pre-processing procedures to better to do better spatial and temporal downscaling. Now, I borrowed this diagram from my colleague Ming Pan to show this the concept of multi-skill information in hydrology. Now, if you think about the forecast, skill of forecast from CFS, you can think about that in a very similar framework. It's very difficult to actually predict what's going to happen, how much rainfall you're going to get at one particular location. But it's relatively easier to predict the average rainfall averaged over a long period of time and the aggregates over a large space. So by including this multi-skill concept in the Basin merging, we'll be able to use CFS forecast and to provide continuous upgrade on the posterior on a daily basis. And it also allows us to do seasonal forecast more frequently. So at the moment, we're actually doing seasonal forecast on a weekly basis instead of doing just once a month. And we also include some of the real-time QPF in the short-term forcing that, in many cases, it improves the short-term forecast. So just give you an example of what do we mean by this, what do we exactly, what do we do? So here's a time series of precipitation that we're trying to predict, all right, so over one location. Now, instead of looking at when it rained and how much it rained on an individual place, we're actually looking at the aggregates. So here's the cumulative precipitation starting from today up to about 90 days. Now, if we look at different aggregates at different temporal scales, so looking at the 5-day accumulation, 10-day accumulation, 15-day accumulation, we can actually derive the posterior distribution of all these aggregates. And then we try to produce a time series or multiple time series that will satisfy those distributions. Now, before we do this multi-scale Basin merging, these are the time series we would actually get. Now, after we adjust that based on the posterior distribution, it will basically go back, it will be much closer to the observation. Now, with that, what we can do is, let me go back one. Now, what we can do is, the aggregates always start from the present day, so it always go into the future. Now, with that, what we can do is, we can always use the posterior distribution from the previous day and as a prior, and then continue to update. Now, one reason that we want to do that is we want to take advantage of what the operational configuration of CFS v2. Now, in real time, CFS v2 produce 16 members each day. 4 of them goes to 9 months from 0Z, 6Z, 12Z, and 18Z. Now, they also produce 3 members going to 1 season from 0Z, and the 9 members going 45 days. Now, advantage of this setting is, it runs every day and it produces a lot of ensemble members. Now, a disadvantage of that is it produces a lot of ensemble members. We have to deal with that. But meanwhile, when we want to use all these members, we have to consider if we put all these members together, some of them are actually older than others. So, some members are 30 days older than what you recently get. So what we're trying to do is we will develop a scheme that it can work on a daily basis and continues to update the posterior distribution using the most recent information. So our current exercise is we'll update all the posterior distribution every day on different aggregates. And then we issue a 90-day forecast as an experimental forecast, 90-day forecast into the future each week. Now, just give you a few examples of this. This is a forecast we made on July 6th. This is 1 week into the future, and we are doing 20 ensemble members. So these are how 20 ensemble members look like 1 week into the future. Now, if you look a little bit further, 5 weeks into the future, 9 weeks into the future, and you start to see that all these members start to deviate. Of course, they should be different. Now, when we get to 13 weeks into the future, now if you compare what actually happened, and some of these members actually show pretty, interesting phenomena, consistent, almost similar to what actually happened. But you also see some members are, very different. Now, a different way of looking at this forecast is to look at the plumes. So in this figure, what we're going to show is, here is the time of forecast. We're looking at the Colorado River Basin, and the black line is what actually happened, the average soil moisture condition over this region. The greens are individual forecast members, and the blue is the forecast ensemble. Now, I'll let this loop start, and you will see each week there's going to be update. And so that's January, that's already February. So you can see that as each week the plume will be slightly different, but most of the cases the actual observation falls within the plume, and sometimes it's closer to the to the ensemble mean, but sometimes it's actually pretty far from the ensemble mean. Now, especially this one, but it's never it's hardly fell out of the entire plume. Now, here comes the very interesting question that we're still struggling. The question is, how do we actually interpret all this ensemble prediction? For example, if this is the actual realization, this is one of the predictions. You can see, okay, it's pretty good over here, but it's wrong over at a longer period of time. And you can do another ensemble, then you do the ensemble average, it might actually get closer. But if you do many of them, you start getting a huge spread. Now, in the end, if you look at the ensemble mean, it's actually, in this case, actually pretty close to what actually realized, what's being realized. But in many other cases, you won't get that situation. You will get a situation like this. The actual observation is similar to maybe one of the ensemble members. So what we learn from here? If we think the system is perfectly predictable, then having multiple members, you will actually end up having an ensemble mean which is similar to what the observation is. So by having multiple members, you are canceling out all the errors. But if the system is unpredictable, the actual truth is just one possible realization of many possible realizations. Now, when that happens is the actual observation will going to be similar to maybe one. But we only know that when it actually happens. So hindsight is always 20/20, but before you look at the observations, we don't know which ensemble member to pick. So what are we trying to do is we're actually trying to develop some scheme to do post-processing. Now, the idea of this post-processing is to do a multivariate linear regression to combine all the ensemble members, see if we can come up with some optimal weights for these members and look at how good they are. So what I show here is a weight for one of the members and look over the Ohio River Basin. And then we check how these weights change over time. In fact, looking at the 6 of these, there's a little change, maybe a little bit of change from one week to another. And this gives us the idea that if we use the weights estimate from the previous week, we can use that to pick up the best prediction or best estimates from the ensemble dataset. Now, so in summary, I think we have already demonstrated some usefulness for our DMAP system, the drought monitoring and prediction system. The real challenge at the moment is how we can actually, the research needs is to improve the post-processing method for hydrological ensemble. Now, also I want to thank my collaborations with my collaborators at Princeton University, University of Washington, and at NCET. Thank you.
Very much. So I think to keep us on time, if you have questions, please contact briefing. So our next speaker is Xiaodong Zhang, and the title of the presentation is Drought Prediction Using GRACE Observations and NOAA Model Simulation.
Thank you. Good morning. And we start this flood or drought study is relatively new. The reason is that recently in our region, North Dakota had a severe drought, so that's we start to look at the drought. And also before I start, I'd like to thank my co-author, Jie and Eric, my student. And the drought, many people have talked about drought, and drought in terms of the impact is the number one hazard, even though the drought seldom cause physical or structural damage. This is the one reason that why drought is take a long time to really realize the drought happening, and sometimes when we really know the drought happening, it's too late. That's why its economic impact is significant. And even look at this picture. This is in November. Even right now, today, last month, 80% of the U.S. is a drought. Actually, most people don't know that. And what we know is Sandy, which is called the flooding in New York, New York area. So it's really important to develop a capability we can monitor and predict the drought so we can mitigate the impact. And this is everybody knows that there are so many different definitions of drought and also different index. And in this, in our study, what we focus is the two index, which are on the top, soil moisture index, deficit index, and the groundwater, or we call the total terrestrial water storage, and derived that from a GRACE satellite to look at how the water storage in the groundwater, how that change. And we use the data and from NASA GLDAS, and we use the NOAA land surface model, and also we use the GRACE satellite data. And for this NOAA model, the data is about one by one GRACE cell, and it's a monthly data from 1982 to 2012. And for the GRACE data, that is also monthly and one by one degree, and from 2003 to 2012. And probably many of you already know that this is how we estimate the soil moisture deficit index and the total storage deficit index. And this is just how we estimate the deficit. And it's easy to understand. We look at, say, for one particular month, let's say May, and we look at the historical range of the moisture, and this is the maximum, this is the minimum. If this is 2011 May, this is the actual soil moisture, we find how much deviate from the median value, and we can do the same thing for the wetness or the flooding. And we have this deficit index, and it's easy to calculate this deficit. We have the deficit, and it's easy to estimate this deficit index for either soil moisture or for the total storage. And this is just an example how the index vary over the time. This is the 2003 March all the way to 2010 March in all areas. It's called the Red River Valley. It's somewhere between, it's a river valley between North Dakota and Minnesota. and over the time to see how the index vary. Also overlay here we have Palmer index, Palmer drought severity index. And we use, if we draw the histogram of the index, we take the 20 percentile that roughly correspond, like if the index is -2, that will indicate the drought. If about 2, that indicate it's extremely wet, there's a flood potential there. And this is the result for the preliminary result for the from March, April, and May in 2012 this year. And on this left column, this is the U.S. drought monitor, and we see there's severe drought in New Mexico, Texas area, and in Florida, Georgia area. And for all the 3 months, this is the index we estimate, use the soil moisture index estimate for those corresponding to the 3 months. And as you can see, this is the soil moisture index is very, very well captured the drought that had occurred during that time period. And what interesting is to see this grease data showed in the deep water or the groundwater. And what we can see that even though, overall the pattern are similar, and we know there's a drought in the southern part of the U.S. and wetness in the northwestern U.S. But what we can see is that the water deficit in the groundwater level is much wider spread, extending almost from coast to coast and cover a much wider area, almost entire southern U.S. And this may suggest that the drought we experienced during this early time of this year has been a long time going, has been going for a long time, but it didn't show up in the surface, but it has show up in the deep water. It has been significantly low level of water over that area. And also interesting to see if you look at the northeastern part, even though on the top soil moisture indicate there's a certain level of drought, but on the groundwater level or deeper level it's not drought at all. It's still pretty wet, or there's a lot of water there. And this is the index. And what we try to do the predict, which is unlike what Dr. Lord suggests, use a different ensemble of climate prediction. All ideas are very simple. We look at the history, and just look at based on the historical climatology, what is the probability for future drought to happen. And the idea is really simple. Let's see, we have this month's deficit index, and we predict what is the probability for next month to have a drought. We see if the drought is -2, we find what is the actual deficit that corresponds or estimate, and from the deficit, we find what is the soil moisture could be, then look at the historical, compare this historical distribution, find what is the probability that the drought could happen for the next month. And this is what we have examples for the March. Again, we did this for all the months but this is just example for the March of 2012. And this is the U.S. drought monitor for March 2012, and this is what the drought actually happening in March. And this is the soil moisture percentile from Climate Prediction Center percentile, and this is the anomaly. And all those indices indicate that there's a drought happening in this area, New Mexico, Texas, and in Minnesota, and in Georgia and Florida area. And this is the result from Princeton data, and overall they capture pretty much very well of what's happening in March. This is the predict in April, and this is our result. And again, our result agree well with Princeton, but overall, but there's a noticeable difference. And in the Princeton results, then it seems somehow, I don't know why, that they couldn't capture what really happened in Texas and New Mexico. They predict very unlikely to have drought, and we use this, our method was able to predict that there's a drought could happen in March. This is we predict in February, 1 month lead time. And the next one we try, again, this is really, we follow the Princeton method or law et al. 2007 to try to predict, instead of look at what the probability of a drought could happen, we look at what the severity of the drought, if drought actually will happen. And the idea again is we follow the Bayesian merge of climatology and the prediction of the prediction of the drought. In terms of the prediction, again, we did not use the climate models. We simply look at the historical data. This is the time series of water balance, the precipitation minus evapotranspiration and the runoff in both surface and deep water runoff. And we look at this water balance over the time series, and we use the auto-regression, integrate the moving average to try to forecast what's going to happen. Given this time series, we try to look at what's going to happen for the next month, next 2 months, next 3 months. And the idea is well established, and the methodology is pretty sound established. And based on those two climatology and what to predict, and we use the Bayesian merger to find what is the probability of the drought could happen. And this is this is the result. We picked March 2012, and this is what the soil moisture anomaly by CPC. And again, we see the soil moisture is pretty low in this New Mexico, Texas area, and Georgia, Florida area, and in North Dakota, Minnesota area. And this is the right panel. This is what we predict. What is the drought severity that could happen in March. And we are happy with the result, and look at particularly in this Texas, New Mexico area, and Georgia, Florida, and particularly in our area, North Dakota and Minnesota, we were able to, all measure was able to predict drought and the severe drought that happened which is actually, it was what happened. And again, this is also agree very well with the drought index that we developed. And if we compare this over the entire U.S., and this is what the predicted drought severity and what observed the drought severity, and again the agreement is pretty good. This is the one-to-one line. This is the ongoing research work, and so right now we are pretty happy with our method, and it was able to predict severe drought occurred early this year. And overall prediction is consistent with the Princeton University result. However, we did find a disagreement, particularly in the New Mexico and Texas area, where that severe drought, it did happen over there. And we try to figure out this next step, what really caused that disagreement. Could Princeton, based on the weak model, and we use the NOAA model, could that the difference is because the different model, or because the methodology we use different from the Princeton University methodology? And looking forward, what we try to do is that we really want to look at over the time period or the time preceding the drought happening, how the surface moisture and the moisture in the deep layer or the groundwater, how that co-evolve over the time, and to find out what could be the dynamic in terms of soil moisture at two different levels. And I think that's the end of my talk. Thank you.
Questions? Very quiet group this morning. Well, all right. Thank you very much. Okay, our next speaker is Denali Fernando, and the title of the talk is Improving Drought Predictability for Application to Water Resources Management in Texas.
Good afternoon. This This work is a collaborative initiative between the University of Texas at Austin and the Texas Water Development Board. Before I proceed, I would like to acknowledge my co-authors, Rong Fu and Bridget Scanlon at UT Austin, Kingsley Moore from NOAA CPC, Ruben Solis and Robert Mays from the Texas Water Development Board, Adam Berman and Lei Yin from UT Austin, and John Mudizhovsky from Rutgers University. The motivation for this work was the 2011 drought in Texas, which I'm sure all of you know had record temperatures and through spring through summer, and it saw 40% of normal precipitation in the year from September through October, that is September 2010 to October 2011, pardon me, October 2010 to September 2011, and really large losses in agriculture. But more interestingly and more important for our work was the rapid intensification in the spring. That was quite unprecedented. Why was the spring intensification a problem for water managers? The plot that you see on the screen on the right-hand side on the left-hand side shows statewide conservation storage in the reservoirs over Texas. The blue line shows you the storage for 2011. What was really dramatic in 2011 was that there was this rapid decline in surface water storage over the state, and the average reduction was approximately 20% in less than a year. That was statewide average, but if you look at regionally, this happens to be the plot for South Central Texas, which is where Austin is located. That decline was even worse. It was something like 40% within a period of 6 to 7 months. And surface water storage across the state reached its record lowest value in November 2011. So such a rapid decline in reservoir storage caught the water managers by surprise, and it really worried them because surface water storage in Texas is designed to cope with multi-year droughts such as that of the 1950s. And if within a year so much storage was lost, that did not bode well for the state, just in case the drought persisted. Okay. So what really happened? Observed rainfall for March to May was at 51% of normal. The plots on top show you the US drought monitor from March through June. So in March, you do see like the western and eastern parts of the state in the D3 category of extreme drought, but it was not really very bad. But then come April, you see a sudden increase in the D3 category and also the worst category, which is D4, spreading over most of the state. And then by June, it's over almost 80% of the state, the worst category of drought, which is exceptional drought. Was the spring intensification predicted? I've taken out plots from NOAA CPC and shown the prediction made in February 2011 for March, April, May temperatures. That does show that in the 2% probability forecast that there was a likelihood of above normal temperatures to the west of Texas and the southwest. But if you look at the precipitation forecast, it does show below normal probabilities, but it's not really marked, and it definitely does not show that it's going to be a rapid intensification. So that led us to ask the question, is spring drought intensification predictable? If so, what were the causes for the intensification of the 2011 drought event? And is this something that was just a rare event, or it's something that is common in other extreme drought events as well? So what we started off by doing was to first look at sea surface temperatures and how they evolved over the year, soil moisture deficits, and surface temperature anomalies. These figures are courtesy of Kingsley Moore at CPC. The first plot shows you the sea surface temperature anomalies for the Niño 3.4 region. Time increases going downwards, and its longitude to the x-axis. So So you see the onset of the La Nina event in the summer of 2010. That persisted until April 2011. Here you see latitudinally averaged precipitation over Texas. So from the fall, you see precipitation deficits around the eastern part of Texas, and then going into April and the summer, the precipitation deficits are over the central part and the western part, and the deficits increase as the spring progresses. And if you look at soil moisture percentiles, you see a soil moisture deficit emerging in the winter, but that intensifies as the spring progresses into summer. So the reds show you the worst categories of the deficit. Then if you look at evaporation, you have a reduction in evaporation at the same time as you see the soil moisture percentiles decreasing. And to compensate for that, you have an increase in sensible heat. And finally, an increase in surface temperatures. The surface temperature anomalies were over 2 degrees Celsius. In some parts, it was almost 4 degrees Celsius in April. These boxes highlight the period which was the worst. And what I'd like to point out to you is that the worst intensities of like soil moisture reduction, surface temperature heating, precipitation reduction, etc., commence in April. And why is April important? April happens to be the start of the rainfall season in Texas. That led us to investigate what could have caused a reduction in rainfall in April. Going into the drivers of spring rainfall deficit, I'd like to point out that the rainfall in the spring can be from frontal systems or convective in nature. So having those points in mind, we looked at drivers that could influence a reduction. So the first thing we looked at was large-scale circulation anomalies. We focused on ridging in the mid-troposphere, 500 hectopascal, due to large-scale subsidence, which could be due to La Nina, and then warming of the atmospheric column. This was from the surface up to 100 hectopascal. What were the temperature anomalies? The data sets we used were NCEP reanalysis version 1. The next factor we looked at was local thermodynamic conditions, and we primarily looked at factors driving convective inhibition. There are 2 excellent papers by Myung and John Nielsen Gammon in Journal of Climate 2010 that identifies sin as a very important variable in summer drought over Texas. So we were interested in finding out how important it was for the spring intensification as well. For this, we used the CFSRR, Climate Forecast System Reanalysis Daily SIN, and we also looked at SIN from the 20th century reanalysis data set because we were interested in finding out whether there were similar patterns in historical droughts too. And finally, we looked at synoptic conditions that may have triggered a sudden rainfall inhibition. For this, we used circulation fields from NCEP reanalysis. Looking at large-scale subsidence, we asked the question, is La Nina the driver for the 500 hectopascal ridge? The 500 hectopascal ridge also happens to be a characteristic feature of drought in Texas. So the figure on the left shows you what the 500 HPA height anomaly looks like in 23 La Nina years from 1949 to the present. You see a ridge over Texas. And on the right-hand side, you see what it looked like for April of 2011. Here, too, you see a ridge over Texas, but it's much stronger than in the composite. And then if you look at column average temperatures, the left figure shows you what's expected during La Nina years. Very warm to the west of Texas, and over western Texas. And then if you look at 2011, a similar pattern, but again much stronger than in the composite and extending into New Mexico. And so the western, just keep in mind that it was extremely warm right here. Yeah. Then if you look at thermodynamic conditions, we saw a sudden increase in convective inhibition in end of April 2011. That's what the red line shows you. And looking at that particular increase in seen at the end of April happens to be quite, it seems to be a common feature in other extreme drought events too, and that's what the orange line shows you. But in 2011, it was much worse than in other years. And the blue line shows you what it would look like in a non-drought year. And because it was a very sudden burst of sin, or a sudden increase in sin, this led us to look at the local circulation features that could have driven this. And what we found was that there were anomalous zonal winds at 850 hectopascal in April 2011, and this drove, and remember that they're flowing eastward over very warm terrain. So that drove an increase in temperature over Texas too. The figure on your left, on the right-hand side, shows you the column averaged wind field. So you see westerlies throughout the column, and you see an advection of warm air eastward, and also anticyclonic vorticity from 700 hectopascals above and above that. That's what the dotted line shows you. At the surface, you see a thermal low. This is due to adiabatic expansion of downslope winds. These would be the winds flowing down from the Rockies. Okay. And then if you look at local, what was happening at the land surface too, you see an increase in temperature at the surface and 850, an increase in dew point depression, and these are the wind anomalies averaged over 850 and 500. You see they are much above climatology. And interestingly, increase in relative vorticity anomalies. That meant that there was a contribution from the lower troposphere in terms of feeding the ridge. So is spring intensification something that's common in extreme drought years? What we found is that there is a preference for dry summers to follow dry springs. And we find that there were 12 out of 18 severe to extreme drought events which had rainfall deficits in all three seasons, that is winter, spring, and summer. And all of these had a common feature that they had stronger zonal winds at 850 in April. And the figure on the right-hand side shows you the composite wind anomalies for those years. And we found that the strengthening of the zonal winds could be predicted with moderate skill at 2-month lead time if you use sea surface temperatures in the Pacific, namely the Niño 4 index. So my conclusions are, soil moisture feedback and strengthened westerlies in spring are key processes in drought intensification. These are primarily linked to La Niña-induced anomalous large-scale circulation in the winter and spring. And what would be the implications for improved predictability of drought intensification? So if we take La Niña-based preconditions, we know that we can use ENSO forecasts for that. The strengthened westerlies at 850 as a drought trigger, we could use Pacific SSTs in February to get a moderate scale forecast of that. But this needs more work because we need to understand the drivers better. For soil moisture, we definitely need investment in continuous monitoring, in situ monitoring, to understand how the deficit evolves. And with that, I'll wind up acknowledging my mentors and collaborators and funding, and I'll take questions.
Any hands up? Okay. I just wondering, was there something peculiar about this La Nina that was just a particularly strong La Nina event that it was had such a big impact?
It was strong, and I think it also persisted until later in the spring. So that could have meant that the circulation anomalies that you associate with La Nina persisted.
Okay, well, thank you. Let's thank all the speakers one more time. It was a very good session. And keep in mind, tomorrow morning we have a poster session, so please come if you can. Thank you.